In this short video, we're going to introduce the NetKernel resource-oriented computing abstraction and show how, when we use the NetKernel protocol, we can distribute trust between multiple parties without incurring n-squared complexity in the number of parties interacting. This is a very simple diagram that summarizes the NetKernel abstraction, the resource-oriented computing abstraction. We have address spaces, and when a requester wishes to interact with another party, they issue a resource request which is resolved by the space to an endpoint which can supply state for the resource that was requested. This abstraction is present inside a NetKernel instance, but it can also be distributed between instances and is the basis for building scalable, distributed, resource-oriented solutions. Here's the context for the demo. This is a very common situation and is sort of the simplest way that three parties can interact with one another. And what we have is a system where party A wishes to make a purchase with party B, but party A doesn't trust party B. So party A requires that there be a non-reputable notarization of the transaction, so that should there be any need, party B can be held account that they accepted the transaction at the price and quantity they were specified. Party A obviously can't trust party B to provide a notary, so party A has to have an independent witness to the transaction, and that's what a notary's function is. So we have a third party, which is the witness, which has a relationship with party A. They're obviously the source of proof for party A. So where the transaction would go in an ordinary system is A would initiate the transaction and say to B, I want to buy something from you. B would say, okay, I have a quantity of those available. A would say, okay, please go ahead and commit the transaction. B would prepare the transaction, but it can't commit because A hasn't got the proof that they have a valid transaction yet. So B returns back saying, okay, I'm ready to commit the transaction. Here's the details. A takes the details of the transaction with the necessary receipt from B, sends it to the notary. The notary signs the transaction with a digital signature, returns the complete signed transaction back to A. A then sends back the signed signature, proof of the transaction, to B, who can then keep a copy for themselves. B can now commit the transaction and then finally return the completed signed transaction to A, saying we've now completed our interaction. So what we see is that this typical approach requires 1, 2, 3, 4, 5, 6, 7, 8 interactions between the three parties in order to complete. We also see that at any point in time, party A, party B and party C need to hold on to intermediate state because the transaction is distributed between these parties, and they need to be prepared to receive back interactions at each point in this cycle. The other problem with this problem is that every party needs to understand how they are interacting in the overall model with each other's party. So B needs to understand that it needs to call back to A and say, I'm at step 2. Party A needs to call back and say, hey, I've talked to the notary, here you are, we're ready to complete. So party B needs to be ready for that. So we end up with lots of small services and small transitions in order to complete the overall transaction. We can see that this is the simplest three-party transaction. As we add more and more parties, we end up getting an n-squared complexity in the problem as it scales out. So what would we ideally like in this system? Well, our overall requirement is that we want an independent witness to a transaction to ensure that we've got legal non-repudiation. To do that, we want it to be as simple as possible, so we want to minimize the total number of interactions, and we also want it to be as trustworthy as possible. And by that we mean we want to minimize the total surface area exposed in the system because it's distributed. And we also need auditability. We need provable boundaries of trust. We need to be sure that nothing else can happen in this system. There's no zero-day vulnerabilities. And of course, it's desirable to make this as efficient as possible. We want sub-millisecond responses, and we would like this to scale seamlessly to n parties. And then for good measure, we want the system to be immune from network communication failure and to be fundamentally asynchronous so that it can support scaling without requiring massive numbers of blocking threads. And of course, all of this we'd like to be measurable. We'd like to actually be able to audit this system and understand that it's doing as we expected. So what I'm going to do is I'm going to show you how we implement this using NetKernel and NKP protocol. And we're going to basically have 3 parties. Each party has an address space, as in that ROC abstraction I showed you. Party A has an endpoint that will initiate a purchase. That can make the purchase to Party B's receiving endpoint in Party B's side. And we'll set up an NKP relationship to a notary so that this notarization endpoint essentially becomes resolvable and available as a resource in Party A's address space. So what we'll do is we'll issue a transaction to B, a transaction request to B, and we'll say, before you come back to me, please ask for the notary service which is resolvable in my address space. So B will make a request here, and in the envelope of this initial request it will be resolved back onto to the requesting side into A's address space, and because A has prepared the address space so that the notary is available, it will get resolved over to the notary. So effectively B is able to make a notary request on behalf of A to the notary in the context of that original transaction. Let's show you that actually working. So here is the demo, and if I run it, what you see is we're making multiple transactions. We're putting the merchant ID in, the purchase ID, and we're getting a digital signature for the transaction, and it runs extremely quickly. What I need to do is slow that down for you, and so we can see what actually happens. So I'm going to use the NetKernel visualizer to record in a time machine debugger the complete cycle of the transaction. So if I run the debugger and issue the transaction and stop the debugger, let's get rid of some of these spurious ones that aren't related to the demo. What we see is that this is the request that I made, NKP 3-party, and I can look at the details of this. I can see that actually it was implemented using Groovy, and the Groovy make purchase endpoint issued a request over NKP which goes to Party B. Now essentially we're waiting for that response to come back from Party B, but while we're waiting, Party B receives that request, prepares the transaction, is ready to commit the transaction, but needs to have it notarized. And we see that we get a request coming back into our address space called Party C notarize, where the notarization is the document ready to be signed, and that goes back out from our address space in A down to the notary in C and gets signed. Finally, that gets returned back to B, and then finally A receives the response to B just here. So that's the view from A's point of view. The interesting thing about this is that A doesn't have to write any code to handle that interaction between B and C. It's just a request that's resolved in the scope of this original request that's gone out to B that hasn't yet received a response. If we look at B's perspective, this is B's receiving the transaction, and we see what happened there. They received the transaction, and we see that B made a request to notarize the request. He doesn't actually know where that is. It's just in the context of this original request. So it actually goes back to A, and B doesn't know anything about C, so it just gets resolved back by A and somehow goes away and is trusted. And we finally get back a response, and then this guy can return its response to A. And finally, if we look at this from the point of view of C, then we see that C receives a party C notarized request. This is coming from B, but routed via A through the contextual address space, and we see that all it really does is make a PKI signature request to sign that transaction record. And we see that it took around about 12 milliseconds to run just the signature. So the total time here was dominated by the actual signature generation, which took 12 milliseconds of the total cycle. It was a 15 millisecond request, so 3 milliseconds inside the endpoint dealing with that B's request. So if we look at the total envelope back up here, we see that the total time to perform the entire transaction was around about 30 milliseconds, of which 12 milliseconds are taken up in the notary, and the rest is just the communication and B preparing the transaction. So it's a very efficient system. So I'm going to show you back in the diagram what's actually happening. So we've seen that it's fast, we've seen that there's very few interactions, and there's no code required by any party in the system to manage that transient state. Let's actually look at the detail of how the system is put together. What we have is some core application which wishes to make a transaction, and we've arranged it so that the core application is completely isolated from the purchase endpoint. We do this for a number of reasons. Notably, we want to minimize the surface exposed to any potential threats in the system, and it's absolutely imperative in any distributed system that your core application is not exposed to the outside world. So what we've done is we've put in place an engineering component that's available in NetKernel called the one-way trapdoor endpoint, and this is, as its name suggests, basically allows requests through but completely eliminates these address spaces from being requested. It's impossible to call back out. All you can do is return a response to the request that comes through the trapdoor. So there's no exposed surface area of the core application at all to anybody in the outside world. Secondly, we make a request with the purchase endpoint, and again this space has no external exposed endpoints in it. It's not like a REST service where you have a web microservice exposed to the outside world. This is completely isolated. It's making a initial client request to B. So B has one endpoint exposed here, obviously because it's got to receive the purchase. And when B makes the notary request to finalize the transaction, it can make the request into its address space. Its address space is contextually linked to this initial transaction request space from A. So the request gets resolved back into A. Now there's something important with that. We must be very careful, because one of the worst attacks we could have would be for A to simulate a purchase back to itself, because it's calling back into this A's address space. So what we've done is we've made it so that NKP is configured such that this purchase endpoint is present on the initial request coming down from the core application and makes a request to A, but this request that's allowable back from B, that endpoint completely disappears from the space in the return call. So there's no actual exposed surface area at all for B to call. There is nothing here. There's only the fact that it can make a request for one endpoint, and that's the notary. And the notary is mapped through an NKP import over here. So B can't do any damage at all to A, and the only thing they can actually call is the thing we want them to do, which is the notary service over here. And then finally, there's a threat that maybe the notary side could be compromised and they could make requests back in here. So we've configured the NKP relationship this way to be asymmetrical. So it's only possible to request down, but the notary can't make any requests back up, just like the one-way trapdoor permits backwards requests. So what we have is essentially a system where we have the absolute minimum exposed surface area to attack. We have no publicly exposed interfaces or APIs apart from this one request to B. we've allowed B to interact with the notary over this dedicated NKP relationship, and so we're effectively delegating the trust for B to interact with party C, but B doesn't interact with any of A's endpoints at all. And then finally, when B receives back the notarization, it can commit the transaction and return it. So what we have is absolutely minimized the total surface area exposed to any danger, and in addition to that, we've turned what was an 8 interactions to do this with a regular a protocol such as REST or any web service protocol. We've turned it using NKP and the ROC abstraction into 1, 2, 3 interactions. But in terms of the actual system architecture, A is unaware of anything to do with the notary, so it's not aware of that in the system. It's just told, this is a resource you must request before you come back to me. So in fact, we've really turned it into one, essentially one simple transaction between A and B, with one additional request made from B, so 2 requests rather than 8 requests. So we've gone from 8 interactions down to 2, and we've got a round trip time of around about 20 or 30 milliseconds, of which most of that time is PKI. We've minimized the surface area down to one single constrained point, so only B is exposed, but that's because B wants to receive transactions. And we've provided an architecture in which we've delegated trust from B to the notary within that unique one-time envelope of trust provided by that initial request. And then finally, the entire architecture is non-blocking. So these aren't physical threaded network connections that we're talking about. These are logical resource requests between these distributed spaces. They're completely independent of threads, and they're completely independent of network connectivity. So in fact, we can completely tear down the network whilst the transaction is ongoing, put the network back, and the transaction will continue without any loss of service. That's the conclusion. Thank you.